Hey everyone! So in this video I like to talk about some problems from the Midterm 1 review activity. So let's start with problem 3, where we're asked to find or write some algebraic expressions for each of these statements. So the first statement says 4 pages longer than half the length of the first draft. 4 pages longer than half the length of the first draft. So there's a lot of keywords in there telling us how we can put the different quantities together. There's also an unknown quantity in there, right? So 4 pages longer than what? Well, than half the length of the first draft. And we don't know what this length of the first draft is. Maybe this is some page count for a book. Maybe they're making a book and it's the first draft of the book. And the length of that first draft is the number of pages in that book. Or maybe it's for a paper that they're writing for a class. But either way, here I'm going to use P to represent the length of that first draft, maybe the number of pages. Right, so again, we don't know this quantity, but it is a number. It is some concrete number, it's just that we don't know it. And we can still do mathematics with this unknown number, right? And so let's write an expression that goes along with this statement here, revolving around this variable p, the length of the first draft. So here it says 4 pages longer than, and so 4 pages longer than is telling us that we're adding on 4, right? It's going to be 4 more pages than something else. And so 4 pages longer than, and longer than what? Well, longer than this next statement, half the length of the first draft. So here let's write this out. So 4 pages longer than something. This is, we're adding on 4 to some quantity. That's what 4 pages longer than is telling us, right? 4 more than something. Well, 4 more than what? It's 4 more than half the length of the first draft. So half the length, or half of anything, is telling us multiply that quantity by 1/2. So what are we taking half of? We're taking half of the length of the first draft. So that's P. That's what we're representing with our variable P. So 1/2 P is half the length of the first draft. 4 pages longer than that is adding 4 onto that 1/2 P. And so our expression is 1/2 P plus 4. So in the next example, it says $101 short of twice last year's price. So here, this is kind of similar. It's sort of in a similar format to above. It says $101 short of something. That's telling us, if I have $3 short of the total cost, that means I don't have the total cost. I'm $3 less than that, or I have 3 fewer dollars, right? So maybe a more concrete example is if the cost of something was like $8 and I was $3 short of having the amount to pay for that, well, that would tell me that I had $3 less than, or in other words, $5. Right, so here I can kind of read this minus 3 as 3 short of 8. And you can read this as is 5. 3 short of 8 is 5. And so here this 101 is telling us we're subtracting 101 from something. But what are we subtracting 101 away from? Well, it's short of this following statement, short of twice last year's price. So again, we have this unknown quantity. It's last year's price. We don't know what that was. Maybe it's the price of some object. But here I'm gonna use P to represent this, and maybe I won't go all out and say what P represents, but I'll just label and underline what P is representing. So P represents the last year's price. So we have $101 short of last year's price, or twice last year's price, or 2 times last year's price, P. Right? Twice last year's price is maybe P plus P, or 2 times P. Either way, it's the same idea, and we're taking $101 short of that, so that's minus 101. So again, it's kind of this funny example where the 101 and short of is telling us we're subtracting away 101. The subtraction is kind of happening in reverse order, right? That 101 is not in front. We're not subtracting from 101. We're actually subtracting 101. It comes after. So the next example says 3 times, so 3 times something, 3 times what? 3 times this quantity here. right? 3 times the following statement. Well, what's the following statement? The sum of the length and 52. Okay, so we don't know this unknown quantity, the length. We don't know, it's some sort of measurement of distance, but here maybe I'll label this with an L. And I'll use a capital L because lowercase l can look like a 1, can be kind of confusing. And then we want to not make, we want to be as clear as we can be, right? So here, 3 times something, so I'm going to write 3 times what? 3 times the sum of the length. And so here, when we say the word sum, it's telling us to add 2 things. So we're going to multiply 3 with the result we get from this addition. Right, sum is telling us to add 2 things, and it's specifically referring to the result of the addition. And so when we're saying 3 times the sum, well, this will be the sum, and we're going to multiply that result with 3. And so the sum of what? Well, the sum of L and 52, the length and 52. So that's our expression for part C. Okay, so these are kind of tricky examples, but hopefully this is helping to clarify some things. Let's look at this next example. We're saying 73% of something, 73% of the difference. And so the difference, just like the sum is saying, the difference means subtraction, but the difference is referring to the result of subtraction. So when we say 73% of the difference, well, we're going to take the difference, whatever it's going to be, get that subtraction out, and then we're going to take 73% of that result. So 73% of the difference of Victor's weight and 100 pounds. So here I'm going to label Victor's weight, I'll label it with a V. And the difference is telling us to take the subtraction, so it's going to be Victor's weight V and 100 pounds. And we're going to take 73% of that difference. So here I'm going to take, how do we take 73% of something? Well, we can multiply it by 0.73, or we can write this as 73 over 100. That's really the same idea, multiplied with, not with V, but with the with this difference. I'm just writing this multiplication to say that that's how we take a percentage of something. Okay, so here we're taking 73% times not just V, but the result of this difference. And there we go, that's our expression. 0.73 times V minus 100, or we can write this as 73 over 100 multiplied with V minus 100. And personally, I kind of like this example better. I think, fractions, they can be a little tricky at first, but they give you a lot of freedom and you can kind of work with them a little bit more easily than you can with decimals. I know calculators really make decimals easy to work with, but when you don't have a calculator in hand, sometimes fractions can be a little bit friendlier actually. So let's look at this next example. It says the graph of an equation is shown below, and we want to identify 4 different solutions to this equation. And so we're not given this equation, and we're not meant to figure this out, but we're told a really valuable piece of information is that the graph of this equation is shown below. And so what this question is really trying to get at is do you know the relationship between equations and graphs? And so, the big relationship is that graphs are they're pictures of the solutions to equations. Right, so for example, I'm just going to make an equation up off the top of my head. If I have y is equal to x plus 3, and I find some solutions to this equation, right? What are some solutions? Well, if I have x and y, and I let x be 5, then what does that make y? Well, here I would plug in 5 for x, add 3, and figure out that the only way that this would be true and I would have a solution is that if y was equal to 8, right? So here, there's a corresponding value of 8 for y when x is 3 to make this equation true, right? 5 for x, 8 for y makes that equation true. Or if I have 10 for x and well, what would that make y? Well, y would have to be 13 to make that equation true, right? We add 3 to x, and that gives us 13. Or maybe -2. If I add 3 to -2, well, that means that I owe $2 and I have $3 to pay it off. I pay it off and I still be left over with 1, right? So y is 1 when x is -2. So these are all different solutions to the equation. And if we imagine graphing this equation, well, what we do is we just make a picture of these different solutions, right? So here, I see there's this solution of -2, +1. Maybe we can include a few more examples. If I have 0 for x, what does that make y? Well, that makes y 3. 1, 2, 3. If I have 5 for x, that makes y equal to 8. I don't know if I made my picture big enough. Let's 4, 5, 6, 7, 8. So 5 for x, 8 for y. Normally, we would kind of make a bunch of evenly spaced tick marks and label the tick marks so that it's clear what the values are on the graph. But here, I'm going through this a little quickly for the sake of time. We want to get through a lot of different problems. But here are some examples of the solutions. The points correspond to solutions to this equation, right? Here, this is the pair 5, 8, and that's because 5 for x and 8 for y makes the equation true, right? And we saw before that, this is an example of a linear equation. If we look at all of the points that make this equation true, they actually all lie on this line through these points, a straight line. Even the fraction or decimal values for x and y that lie on this line, they're solutions to this equation too. But anyways, that's really what I want you to see when you see a graph, is really just a picture of all the solutions. So, maybe I look here and I see that at 4, at x is equal to 4, I have a y value of 7. Right? And that kind of makes sense because when x is 4, I add 3 to it to get 7, and that gives me my y value. Right, so really, I can look at my graph, see the different points, and those tell me solutions to the original equation. Just like I can go in reverse and start with the equation, find solutions, and plot those to make my graph. A graph is a picture of the solutions, and so if I want to identify 4 different solutions to this equation, well, here, these are really just asking me to identify some points on this graph. Those are going to be solutions to whatever the equation is, even though we don't know it. And so here, let's just pick a few points. So, one point that really stands out to me is, well, there's nothing really special about this point, but maybe let's just identify it. The easiest ones we can really point out are the ones where the grid lines cross. Here's this point 6 for a horizontal coordinate and 8 for a vertical coordinate. So x is equal to 6, y is equal to 8 if x represents our input variable and y represents our output variable. So 6, 8, this ordered pair, this is a solution to our equation, even though we don't have the equation. Or 10, 0, right? So 10 for x, 0 for y. Right, and it's 0 because when we look towards the 0 for y, because if we look towards the y-axis here, that's where we lie in relationship to the horizontal or the vertical axis. The y-axis is at a y-coordinate of 0. We can also notice that there's this point here. This is another solution. This is another point on our graph. It's the point 2, 8, and so that means it's another solution to our equation, whatever it is. And then we can also see that there's this point at the very top. This is another example. This is 4, 9. And so, this equation, maybe I'll tell you right now, I kind of just made this up for this example, is 1/2, it's x minus 4 squared plus 9. And so you're not meant to know how to create this equation, and you might not feel even comfortable evaluating different x values in this, the right-hand side of this equation. But if you are, it might be worthwhile to verify that really these points here do make this equation true. So even though we didn't know it, we found these different solutions just by knowing that points on a graph are solutions to the equation of that graph. So this next example, we're asked to evaluate the expressions at the given value. So we're given a bunch of different expressions, and they have different variables in the expressions, and we're told to compute the result when we plug in these different values for the variables. And so here I'd like to go over one example. Let's go over part C of this problem. So here this says we've got the expression 3w plus z all over z. And so what we're going to do is we're going to replace w with 8. And we're going to evaluate this expression at w is equal to 8. And I'm going to replace z with 6. And here when we say replace z with 6 or z is equal to 6, that means everywhere I see that variable z, I'm replacing with this value 6. And I'm including parentheses just because it's typically good practice to wrap your substitutions when you're evaluating an expression, wrap those replacements that you've made with parentheses. Okay, so here when we have a numerator and a denominator, this big fraction bar, splits up the numerator and denominator, so we want to evaluate the numerator on its own and the denominator on its own first, because that's just how order of operations works with fractions, is that fraction bar kind of groups things and separates things out. So let's simplify that numerator, and so order of operations tells us to perform the multiplication before the addition. So I'm gonna multiply 3 and 8 together to get 24 plus 6 over 6. And then 24 plus 6, that's 30. And this is all over 6. And now 30 divided by 6, this is just division. It says how many times does 6 go into 30, and that goes in 5 times. So this is 5. And so you might look at this fraction here and sort of think to yourself, oh, I'm very comfortable with reducing fractions. I might want to reduce here. I would definitely encourage you not to. Usually it's a good idea to wait until your numerator is completely evaluated out and your denominator is completely evaluated out before you reduce your fraction. You try and reduce your fraction. It turns out that when you try and divide two quantities, this denominator here is really dividing every single term, and it's a common mistake that students make, is that they try to divide it into one term. And so that definitely leads to a wrong result. It's kind of like, it's sort of based on order of operations. Maybe I won't dig into this too much. I think it's kind of a little bit of a tangent, but let me just encourage you to evaluate the numerator as much as you can, evaluate the denominator as much as you can before you try and do any reducing with fractions. So this wasn't on the review activity, but this was requested by someone on the survey, so I'm gonna write this out and work through. So let's evaluate the expression 8 times x plus x times y at x is equal to 1/2 and y is equal to -6. Right, so here we have this expression, and we want to replace x everywhere we see it with that value 1/2. We want to replace y everywhere we see it with that value -6 and compute the result. So here let's go ahead and do that. This is 8 times, this is 1/2 for x, plus 1/2 again for x, multiplied with -6. Right here it says x times y, right? X and y without any operation together, that's telling us to multiply these two things. So although there's this negative sign, that's not telling us subtraction, it's just saying multiply with the negative number 6, -6. And then I have to wrap my parentheses there to really say, hey, this is the first thing I want to compute. Right? Parentheses tell us, do this first. And so let's do that. So here, there's still 8 outside the set of parentheses, and we want to evaluate what's inside the parentheses first. Again, still following order of operations. So we're going to start by doing this multiplication before this addition here. And we have 1/2 times negative 6. And so 1/2 times anything is telling us to take half of that quantity. So, what's half of negative 6? Well, it's negative 3. But, you might feel unhappy with that, and you want to see the mathematics more of this, just to really feel convinced. I know it's a believable argument, but sometimes it's helpful to really see all the computation laid out so that you can do it in the future for more complicated examples. And so, in this example, when we want to multiply two fractions, and one of them is a fraction, one of them is a whole number, it's helpful to write that whole number as that whole number divided by 1. Right? Anything divided by 1 is itself, so I'm going to write this as negative 6 over 1. And when we multiply fractions, we multiply straight across. This is negative 6 over 2. And negative 6 over 2, well, this is just saying, take negative 6 and divide it by 2, which is negative 3. Right, so when we multiply or divide two numbers, if their signs are different, then the result is going to be negative. So that's going to give us this negative result, and then 6 divided by 2 is 3. So we've got 1/2 plus negative 3. Now what's 1/2 plus negative 3? Well, here, if I want to add two fractions, I need to make a common denominator. And so, actually, it might have been beneficial to leave this as negative 6 over 2, right? So here, negative 6 over 2, we've just shown is the same as negative 3. And we reduced it because, it felt like it would be a nicer value or a nicer result. But actually, it turns out that, here, if I want to add with the fraction 1/2, negative 6 over 2 has that same denominator, and that's the form of it that I can add with 1/2. So let's go ahead and do that. So this is 8 times 1/2 plus negative 3. Well, we just said negative 3 is the same as negative 6 over 2. Right? Negative 3 is the same as negative 6 over 2. I'm just writing it in this form because we have a common denominator, and to add fractions or subtract fractions, their denominators need to be the same. Okay, so here, if I want to add these two fractions, if their denominators are the same, I can just add their numerators together. So I've got 1/2. Actually, I'm just going to write this as one single fraction. This is 1 plus negative 6 all over 2. So this is 8 times 1 plus negative 6 is negative 5. If I have $1, I owe 6. That comes together as me owing $5. And then this doesn't reduce, but I can multiply with 8 now, which I can, as we saw above, when we multiply fractions, we can write that 8 as 8 over 1, multiplied with negative 5 over 2. Actually, maybe I won't write these parentheses here. So here this comes out to be negative 40 over 2, right? 8 times negative 5 is negative 40. And then negative 40 over 2, that's negative 20. And so that's the result. So that's a very full problem. Hopefully you followed me the whole way through. And if not, I definitely encourage you to look back or send me a message on it. I'd be happy to expand on this. There definitely were a lot of steps in here. Okay, so let's work through some problems some parts from problem 10. Let's start with 4D. Oh, I covered some of the problems. So 4D, we want to solve the equation 4 minus 2z over 5 is equal to 8. And so when we're solving these equations, one good practice is to try and get that variable completely alone, right? Because when we want to solve an equation, we're trying to find the value of the variable that makes the equation true. And if I can get, my equation down to, in a fair way, that variable alone, it'll tell me what number that variable is equal to. And so let's go ahead and do that. And so usually when we're trying to solve an equation and isolate a variable, we want to sort of unwind what's happening to that variable. Right? So you kind of look at this equation and that variable z here. Actually, maybe I'll point it out in the equation I rewrote. So we want to get that z variable isolated. We want to start undoing the things that are happening around z. Right? So if I imagine plugging in a value for z, what would the steps be that would occur to that number, well, first it would get multiplied by 2, then it would get divided by 5, and then we'd subtract that from 4, right? So, I can kind of think of, we would multiply this quantity by negative 1, and then we'd add it with 4, right? That's what subtraction is adding the opposite. And so here, if I want to reverse this, I want to reverse these steps, well, really what I want to do is I want to subtract away this 4, get rid of this 4 that would be added on to this result at the very last step. I would undo this with subtraction by 4 to both sides. Then I would undo this division by 5, and I would undo this multiplication by 2. And that would get my z variable very close to being alone, and we'd be able to identify what that value of the variable ought to be to make the equation true. So when we're solving equations, we want to isolate the variable by removing everything that's happening around it, applying different things to both sides, but we want to choose the things to do to both sides in reverse order of operations order. So, usually we typically, multiply and divide before adding and subtracting. When we're solving an equation, we want to add and subtract to both sides of the equation before multiplying and dividing. Okay, so let's go ahead and subtract away 4 from both sides of this equation. And when we do that, we get negative 2z over 5 is equal to 8. Okay, so this was subtraction before, but again, you can think of subtraction as adding the opposite, so you can kind of think of this as a sort of plus negative 2z over 5. Right, so we've got negative 2z over 5 is equal to 8 once that 4 is gone. And then we can multiply both sides by 5. Right, so here I've got negative 2z divided by 5. If I multiply by 5, it's going to undo that division by 5. But again, I have to do it to both sides of this equation. Oh, I kind of made a mistake. I didn't actually subtract 4 from the right side earlier. Right? I can only subtract 4 from the left side if I'm going to subtract 4 from the right side. You can kind of think of this equation as sort of a balance beam, and you can only really manipulate this equation by sort of applying the same steps to both sides of the equation. And so if I'm going to subtract 4 on the left, I have to subtract 4 on the right. This gives me, this was just from the previous step. I still haven't multiplied 5 to the right side either, so that would come next. So multiplying by 5 to the left side undoes the division by 5, and I'm left with negative 2z is equal to 4 times 5, that's 20. And then now I would divide both sides by negative 2 right here. This is negative 2 multiplied to z. And to undo this, I would divide both sides by negative 2. And you might feel encouraged to add 2 to both sides because you see this negative sign. But that would actually be incorrect because this negative 2, it's not being added onto, or it's not being subtracted from z. It's actually being multiplied to z. And so if I want to get z alone, I should undo that multiplication with division. Okay, and so we found our solution now. Z is equal to negative 10, right? 20 divided by negative 2, it's like 20 divided by 2, and since the signs are different, the result will be negative. And so let's verify this. Let's check. We've done a lot of work here, and it might feel like this result kind of, there are a lot of kind of weird steps in this example, so it's worthwhile to check that really this does make the equation true. Check the solution. And so what does that mean? I want to plug it back into my original equation just to verify that the left side comes out to the same value as the right. So we've got, this is, it was 4 minus 2 times z over 5 is equal to 8, right? So we want to check this when z is negative 10. So we got 4 minus 2 times negative 10 over 5. Does this equal 8, right? We don't know if this is really true. We've kind of, we're under the impression that it's true. And we've found enough reason to believe that it's true, but let's verify this. So this is 4 minus 2 times negative 10 is negative 20 over 5. Is this equal to 8? Well, we got 4 minus some quantity. What's negative 20 divided by 5? Well, that's negative 4. Okay, 20 divided by 5 is 4. Negative 20 divided by 5 is a negative 4. And is this equal to 8? Well, if I'm subtracting -4, that's like adding the opposite of -4, so that's like adding +4, and 4 plus 4 does equal 8. So really, this is truly a solution to our equation. So all the steps we did above, they really are valid. So in this last example, we're asked to solve the different inequalities below. And so, the first two, there's just a single inequality there. And solving these is a lot like solving your typical equations, but with one little extra fact, right? So when it comes to solving inequalities is like solving an equation, but maybe I'll add the little extra fact is that when multiplying or dividing both sides of that inequality by a negative number, the inequality sign must be flipped or reversed, right? So we would, if we, for some reason we wanted to multiply both sides of this inequality by -1/3, or if we want to divide both sides of this inequality by 3 at some point, by -3 that is, sorry, then we would have to take this inequality sign and change it from greater than or equal to a less than or equal to sign, or a less than or equal to sign to a greater than or equal to sign. And so here, maybe let's go through one of these examples just to really showcase how this works, right? So here, if I have 2 minus 3z is less than or equal to -7. Well, I want to get this 3z alone, -3z, or I want to get this z alone. And so I'm going to subtract away 2 from both sides. And this gives us minus 3z is less than or equal to. And now what's -7 minus 2? Well, this is -9, right? Not -5, it's -9. If I owe $7, and this is a lot like -7 minus 2 is the same as -7 plus -2. If I combine these two negative numbers together through addition, that's like adding two debts together and giving me $9 of debt. And then if I want to get the z alone, I'm going to divide both sides by that -3, giving me z is, well, here maybe let me compute the right side. -9 divided by -3 is +3. And then we would reverse that inequality sign. So z is greater than 3. And if I wanted to draw a picture for it, there's this number line. Here's 3. And just to have this picture, the solutions would be, well, z is included, or the z is equal to 3 is included because this is greater than or equal to, and so z is equal to 3 is a solution. But also all the values above 3, greater than 3, make this inequality true as well. And so those are the solutions that, or values we can plug into this inequality and make the left side less than or equal to the right side. Right, so we can plug in 3 because we're allowing for equality here. It's greater than or equal to. And we could plug in 4, 5, 6, and so many other values just as long as they're greater than 3. And notice, usually usually we'll be solving equations and we're used to seeing z on one side and 3 on the other. That's telling us that 3 is the solution. But here in this case, it's all values greater than or equal to 3. Now, if we didn't have this greater than or equal to sign, it was just z is greater than 3, then 3 itself would not be a solution that would work. Right? 3 would not actually be a value that makes the inequality true. And so despite seeing z here on the left and 3 here on the right, 3 for our variable would not be a true solution. It's just kind of telling you what the solutions are. It's saying that actually values that are larger than 3 make the inequality true. In the case that this is not greater than or equal to, that it's just greater than. Okay, so z is greater than or equal to 3. Let me do this another way just to show you that there are multiple ways to do this. and they really amount to the same result. So, one thing I can do is I might notice that there's this minus 3z here, and I'm not so happy with it being minus 3z. One thing we can do to make that a little bit friendlier is we can add 3z to both sides so that it's no longer minus 3z, right? So 3z is some number, and I can add it to both sides just like I can add or subtract negative 2 from both sides, or add negative 2 to both sides. And so when I add 3z and it's subtracted as well, then those are going to undo each other on the left. And I'm just going to have 2 is less than or equal to negative 7 plus 3z. And if I want to get 3z, or if I want to get z alone, I'm going to get rid of this subtraction of this negative 7. I'm going to add 7 to both sides, right? So it's going to be plus 7, and I get 9 is less than or equal to 3z. And then the last step here is to get z alone, I would divide both sides by 3, giving me 3 is less than or equal to z. And here I wouldn't flip the inequality sign because I'm not dividing or multiplying by a negative number. And so we have 3 is less than or equal to z. And this is kind of a confusing statement to look at. But what are the values that make this inequality true? Well, z is equal to 4, z is equal to 5, right? 3 is less than 4, less than or equal to 4, 3 is less than or equal to 5. Really all the numbers that 3 is less than, right? So I can write 3, and really all the numbers that 3 is less than, or well, these are the numbers out here. These are the numbers that 3 is less than, right? 3 is less than 4, 3 is less than 5, 3 is less than 6, all these values out here. So we get a different looking inequality, but I just wanted to show you that we get the same inequality, we get the same result, the same solution set, even when we try and solve this inequality in a slightly different way. And so the last example I'd like to go over is one of these inequalities below, where there's two inequalities floating around. And so these are called compound inequalities. And we really do exactly the same thing, but instead of just doing things to two sides of an inequality, well, there's 3 different sides to that inequality. And so we would just want to make sure we perform operations on all 3 sides whenever we do them. And we want to get that variable isolated and alone, sort of in reverse operations order. So if I want to get x alone here, I'm going to subtract away 5 from both sides, well, all 3 sides. And this isn't going to change my inequality signs because, well, it's not multiplying or dividing by a negative number. And then here I have multiplication by negative 2 to x. So if I want to get that alone, that x variable alone, I'm going to divide all the sides by negative 2. And so we get 2 divided by negative 2 is negative 1. Negative 2x divided by negative 2 is just x. And then 8 divided by negative 2, well, that's negative 4. And here this reverses all of the inequality signs as well because we divided by that negative number. And so this gives us negative 1 is greater than x, which is greater than or equal to negative 4. And this is kind of a confusing way to write it. It's really just the same way that these two inequalities are the same. They represent the same idea. That one is just the complete reverse of the other. We swap the sides and we flip the inequality. Well, we can sort of rewrite this inequality here as negative 4 is less than or equal to x is less than negative 1. And I think this is a clearer statement to read than the previous example. You can test different values and see that they're really the same, and I encourage you to do that, but I think it's easier to read this way. And so this is really going to read as all the values between negative 4 and negative 1 that include negative 4 but exclude negative 1. Right? So if I kind of draw out a number line, negative 4 and negative 1 are kind of the stars of the show. And we're really saying all the values between negative 4 and negative 1 are going to make this inequality true, but not including negative 1, so we put an open circle there. And including negative 4, right? Negative 4 is less than or equal to x, so we're allowing for equality of negative 4, but it's just less than, not equal to, negative 1. So we can plug in things like negative 2 and see that it makes the inequality true, But if we plugged in -1, it would not make the inequality true because -1 is not less than -1.